Okay, so my name is Ian Spielman. That's what the I is, Ian. And I was originally scheduled to talk about something called quantum devices, and there will be some stuff about quantum devices in here. But owing to a lack of preparation, I'm instead going to tell you about some of the kind of basic physics that we do and how we do that kind of thing in the laboratory. All right. So hopefully by the end of my little expose today, you'll know what a gauge field is and how it can meet a Bose-Einstein condensate. Maybe know about some of those things independently as well. So the first thing you got to know is that I'm an experimentalist. That means there's a laboratory and we do stuff in the laboratory. So these are some pictures of some stuff we did. So what are these pictures of? These are pictures of what I'm about to tell you about, which are Bose-Einstein condensates. So these are going to be little nuggets of atoms. I mean, really little, like maybe 10 or 20 microns across. And they might have a couple million atoms in them. So that's what we're going to talk about. Ultra-cold atoms that are really quantum mechanical. All right. All right, so the first thing is a BEC. I'll tell you what a BEC is, but here's the important part. It's extreme quantum matter. It's some of the coldest stuff that exists in the known universe. So somewhere else there could be colder stuff, but as far as we know, it's pretty much the coldest. And not only is it ultra cold, it's ultra quantum. So at the Joint Quantum Institute, ultra cold isn't cold enough. That's just cold. No, ultra quantum is what we're after. I'll tell you about that. What does quantum mean at all? All right. So what I'll be telling you about now is a little bit about how to think about BECs in terms of just talking about waves and stuff like that. So I think everyone's familiar with the wave, like there can be a wave in your bathtub. You paddle your hand up and down, you get some waves coming out. Those are pretty boring waves. But by now, everyone knows that something as simple as my laser pointer is a wave. And I happen to notice the cute diffraction gratings up here, and you can diffract the light off of that, and that's sort of telling you about the wavelength of wave nature of light. But maybe that's not so surprising that it can be a wave, because it doesn't weigh anything. You sort of look at it and you can imagine an electric field going zoop to zoop to zoop, not weighing anything. But what's really more amazing are things that have mass and also act like waves too. Now maybe you're tired of being amazed by this. I mean, the idea that an electron can act like a wave, well, that's more than 100 years old now. So this is an image of a diffraction pattern of electrons as they went through a multiple slit diffraction pattern. And what you see is that the accumulated density of dots is higher here and lower there. So even though the electrons came at these guys one at a time, nevertheless, you could see that they were acting like waves, interfering like waves do in the same way that the light did. All right. But really, an electron doesn't weigh very much, like 10 to the minus 31 of a kilogram. Okay, that's really tiny. I'm willing to stretch my imagination and say, well, that's just basically zero. But you can make ever heavier things that also act like waves. So maybe 15 years ago, the same type of experiment, a double-slit interference experiment, was performed with carbon-60. Right? So this isn't an electron. This is made out of a bunch of electrons comprising 60 carbon atoms. And nonetheless, a beam of these C60 molecules sent through two slits diffracted off one another in exactly the same way that the electrons diffracted off one another, or in the same way that the photons comprising the light can interfere with one another. All right? So this is pretty amazing that if we really work hard to make things ultra cold, really get rid of all the temperature, the excitations out of the system, everything we've ever looked at is quantum. Okay? When it's cold enough, there is nothing we've discovered in nature that doesn't act quantum when you make it cold enough. That's pretty cool. So what's the guiding principle? Like, how should you know if something's going to be kind of quantum or kind of not quantum? Well, a good guiding principle is the Heisenberg uncertainty relation. You've probably heard about that, maybe when you're in kindergarten or something like that. But the basic idea is what's these little triangles? Those are deltas. This is saying that the uncertainty and how well the position isn't just known, how well the information about the position even exists in principle. You take that uncertainty and multiply it by the same uncertainty and the momentum, or which is the velocity. And this always has to be bigger than some number, and that number is Planck's constant. Now, Planck's constant is like a totally tiny number. So we don't really see this very much in the real world. But I want to emphasize a point. This isn't the uncertainty in how well you know the position. You could know the position extremely poorly because you had a very bad meter, your eyes were blurry. No, this is the uncertainty in how well in position the position is knowable. All right? And likewise, this delta p is the uncertainty of how well the momentum of the particle is, even in principle, knowable. All right? So you might have a situation where you know with high precision where something is, where its position is highly knowable. That means its momentum is highly unknowable. It doesn't even in principle exist. And the product of these two in principle existness is the Heisenberg Planck's constant. All right? Now, it's really small. This is, again, the sort of the 10 to the minus 30 something number. It's like the mass of the electron is 10 to the minus 31 kilograms. Here we're having 10 to the minus 34 joules times seconds. Man, that's small. So you have to work hard to see the Heisenberg relationship. And that sort of is addressed by a question like this. Why don't you see it in everyday life? Well, we can turn the momentums into velocities, right? M times v, that's a momentum. And I'll make a little equation. And this equation is exactly the one I showed you before, but now relating the uncertainty in velocity and the uncertainty in position. All right, so if you take a 100-kilogram person, which is a touch on the heavy side, I'll grant you, sort of walking also pretty slowly, as a person of that mass probably would, the uncertainty in position of that person is 10 to the minus 36 meters. That is like incredibly tiny. That's tinier than the hydrogen atom. That's tinier than any component of the nuclei. You couldn't even in any way know the uncertainty of that person. And even if you get a lighter person, and admittedly this particular person moved relatively rapidly, you never see anything that looks like that. Of course not. You just see this. Okay. So in everyday life, quantum mechanics is really hard to come by. And it's not because nothing is quantum. No, everything's quantum. It's just because everything is so big that you just really have to work hard to find your quantum mechanics. And you either do that by working with things that don't weigh very much, or by cooling it down, so really you have a very it's moving really, really slowly. And that's what this talk is going to be about. It's about taking regular everyday stuff and making it really dang cold so quantum mechanics can be important. All right. So here are some examples of things that I won't talk about, some of which you'll be seeing over this afternoon and maybe later on, things that are quantum mechanical. So what this is a photograph of is called an ion trap, and you'll be seeing some ion traps later on today. And what this is a photograph of light scattering off of individual atomic ions. These things are atoms with either one too many or one too few electrons, in this case one too few electrons. So someone has forcibly extracted an electron from an atom, making it into an ion. And now this ion has an electrical charge, and you can trap it with other electrical charges. So a combination of static and dynamical charge voltages make this ion trap. So that's just one atom, one ion. These guys are really quantum mechanical. And I would say the best quantum mechanics experiments really looking at entanglement, uncertainty, quantum information, that stuff is typically done with these atomic ions because they can be controlled so well. This fancy looking part of the figure, I didn't really want to look at any of the details here because that's really complicated. But one thing I do want to point out to you is this sort of weird schematic over here. And what that's meant to indicate is the energy landscape that these ions are sitting in. And what's this a picture of? It's a picture of the potential energy. That's, you know, as a physicist, a harmonic trap is a harmonic, 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 like all we say. This is a trap, like a pendulum or something like that, the landscape that this ion can move around in. And the really awesome thing this sort of depicted here are these horizontal lines. And what that's telling you is that atomic ion can only exist with those particular energies. So the energy, in fact, can be knowable with perfect precision. And each of these particular energy so-called eigenstates are associated with some positional distribution of the atom or the ion. All right? So you'll be seeing in the flesh, if you will, an ion trap like this later on. This is an image of another kind of system that, if you look at certain degrees of freedom, is extremely quantum mechanical. This is a superconducting circuit. So the little, this one's probably made out of aluminum. And the really important part is these wiggly traces back and forth there. These are meander lines, and inside these meander lines you can have standing waves. And these standing waves can have quantum mechanical degrees of freedom exactly associated with the energy levels in the atomic ions harmonic trap. All right, so this is another system, a superconductor, that I know you'll hear about some tomorrow, that can also be extremely quantum mechanical. Okay, great. So for the purpose of this talk, I want you to learn a little bit more about the particulars of quantum mechanics. So if I have just one quantum mechanical thing, like one electron, or one atom, or one photon, I can describe that quantum mechanical thing pretty simply in terms of what's called a wave function. So how many people here know a little bit about wave functions? Like sometimes you call them by psi. It's sort of that level of knowing. Okay. So the wave function is a mathematical function that tells you everything that you could possibly predict about a quantum mechanical system if you ask the right questions. So this blue line here is plotting probably what you ordinarily think about a wave function. That part of the wave function is telling you, it's called the probability amplitude. But functionally, it's telling you what the probability, if you cared to measure, of finding a particle would be, right? So this particular wave function is describing, let's say, a single electron or a single atom. And the width of this distribution is exactly the thing I was telling you about before. It's the uncertainty that even in principle, you could know where that particle is. Why is it? The wave function is the complete group of information about that particle. And in principle, it doesn't have a well-defined position at all. Okay? That's sort of the graphical representation of the Heisenberg uncertainty principle, is that this width is telling you how well, in principle, does the information about where that thing is live. Right? That's the probability distribution. And it turns out that's not depicted here. The width of this is also associated with its motion, and I wasn't going to describe that. But these wave functions have another degree of freedom that often is not talked about, but it's crucial for what I'll tell you about today. And that is, it's not just a number giving a probability. Every point on here also has an orientation somewhat like these clock faces. Mathematically, this is a complex number, not a real number. And what that means is it has an amplitude associated with the probability and a phase, just like the time on these clocks. All right? So a wave function is described by more information than just a probability. And in fact, it's how these clock faces are twisting that tells you about the velocity of this particle. So somehow the velocity is encoded in these clock faces, and where it is to a large is encoding mostly by this blue curve down here. All right. So a wave function has these two parts, and I'm promising to tell you a little bit about gauge fields. And maybe you've heard about gauge fields when you hear about high-energy physics, but interestingly enough, they're also related to clock faces. And hopefully by the end of this talk, you'll see a little bit about what that's about. All right. So you may have noticed, if the clock faces change a little bit, you can have exactly the same probability distribution. You would find that particle in exactly the same place. But with these new positions of these new clock faces, it's now moving in a different way. All right. So that clock information, so-called phase, I'll probably call it the phase later on because that's what sort of a physicist would call it. This phase is telling you something important and physical about the system. It's predicting or giving you the ability to predict what this wave function is going to do in the future. All right, so that's sort of the introductory thing. You're going to see some of this going through the talk. And now I want to tell you about Bose-Einstein condensates, what they're about, how we make them, and how cold is ultra cold, and when they actually get to be quantum and like wickedly quantum. All right. So hopefully this is a slide that you all know about. So this is the usual phases of matter that you're going to learn about in school. Although I have a son who's 12, and the weirdest thing, he said, Dad, I learned about the phases of matter today. I said, oh, really? Yeah. When I was in school, plasma, I thought that was a pretty exotic phase of matter. He was like, no, Dad, there's one more. It's called a Bose-Einstein condensate. I'm like, really? They told you that in class? He's like, yeah. There's 5 phases of matter. I'm like, okay, 5 of them. Well, we'll go with that. So maybe these days it's just like in school. But anyway, the basic idea is a plasma is not exactly a distinct phase of matter, but it's a phase where the individual atoms making up a gas begin to lose their electrons. So it's a partially ionized gas. And of course, the gas is a little bit cooler than the plasma, and this is just the usual motion of particles bouncing off of each other. You put it in a box, they sort of poof outwards. A liquid, make it a little bit colder, these things will condense and form a liquid exactly as you're used to. And if you take an ordinary chunk of stuff and make it yet colder, it's just going to turn into a solid. Right? You sort of experience with this. You take an ice cube, it melts. You put it in the pan, it boils and goes away. There you got 3 of these 4 phases of matter. Incidentally, can anyone find a plasma in this room? Yeah, I've got one. Yeah, inside the fluorescent bulbs, you have some plasmas. So yeah, so plasma is certainly part of everyday life as well. You just don't, if you break it, of course, it goes away, so it's a bit disappointing that way. But if you work hard, if you sort of frustrate these particles' ability to get close together, then you can avoid the liquid phase of matter and you can avoid the solid phase of matter. Right? So if you sort of think about a liquid, it's just these atoms have gotten kind of close together and they can still sort of move around like this. And they slow down a little bit and they form a solid. So if you make sure they can never get close together, if it's always a gas, we as physicists can ask the question, what happens to this system if it's always kind of gaseous? All right? So here's my little cartoon of what a gas looks like. Right? I have little circles. Those are supposed to be atoms. And they have little arrows coming out of them, vectors. These vectors are telling you where the atom that's located here, what direction it's moving and how fast. But you need to be reminded, right? I told you we have Heisenberg's uncertainty principle. So even in principle, you can't possibly know exactly where the atom is and also know how fast it's going. You don't have access in principle to that information. So for any particular gas, you can ask yourself the question, how far away from violating Heisenberg's uncertainty principle is this gas? Given the sort of typical velocity in the gas, so we'd say the spread of velocities really, how well is the position defined? All right? So in this, and that quantity is called the thermal de Broglie wavelength. Given the range of velocities in the gas, how well could you possibly know the position? So at room temperature, a typical gas has a velocity of about, say, 300, 400 meters per second, which interestingly is similar to the speed of sound. And anyway, the associated length scale, the Broglie wavelength, is, I wrote it down here, it's 2.5 picometers. That's 2.5 times 10 to the minus 12. Okay, and that's really small. That's smaller than any of these atoms anyway. So this gas is just going to be a gas, and for all practical purposes, you could, in principle, know where the atoms are of that gas. In practice, of course, there's billions upon billions of atoms, and even the tiniest volume, you couldn't, in practice, know where they are. But you could, in principle, know, for all practical purposes, where those were. All right. Let's see, some other things that I wanted to mention here. So the thermal de Broglie wavelength is telling you about how well, in principle, you could know where the atoms are. In a typical room like this, how far apart are the atoms? The scale of the separation is a couple of nanometers. All right, so they're pretty far apart compared to how well you could possibly know where they are. So I call this to be a classical gas. It's a gas where you didn't need to know about quantum mechanics to know basically what it's doing. So now you take this gas and you frustrate its ability to form into a liquid. And how we do that is keep the density pretty low so that there's never a chance for two atoms to stick, in fact. And I can tell you, is anyone curious about that? How do you keep atoms from sticking? Or even better, what makes atoms stick? So if you take two like billiard balls and bounce them off each other, do they ever stick? No, and the answer is no. And why not? It's because in physicist lingo, the energy is conserved and the momentum is conserved. So if I look at if I close my eyes, if I throw them at each other, I close my eyes and open them again a little bit later on, I know that energy and momentum is going to be conserved. And with just two objects, you can't have equal and opposite momentum, let's say, and make them stick. Because at the end, they're going to be stopped. And what's the energy going to be? It's going to be zero. So you can conserve the momentum, plus and minus is zero, but then you lost the energy conservation. So in order to get things to stick together, to begin the process of forming little droplets or little chunks of solid, you have to have another way to conserve energy and momentum. And what we call that is being multi-body collisions. So if you have three things, I really can't do my foots, okay? But if my foot comes in and collides like this can stick together, and this guy can go flying out real fast, thereby conserving energy and momentum. So you need what are called three-body collisions in order to ultimately, or four-body or five-body, to make teeny tiny droplets. So we thwart that process by making the density so low that pretty much there's never three-body collisions. All right, that's sort of our trick for doing this. And if you do this, you can take a cloud of atoms and cool it and cool it and cool it and never have anything that's a liquid, never have anything that's a solid. And now we can ask the question, what happens when you do that? Well, room temperature in my favorite unit system is a 300 Kelvin. If you take this and cool it down to 1 Kelvin, and I'll tell you how cold that is in a little bit, but that's pretty cold, I can compute the Broglie wavelength quantity again. And it's gone from 2.5 picometers to 43 picometers. That's pretty small, but it's getting to be not terribly small. So we cool this yet further until the point happens, this is at hundreds of nanokelvin, that's 100 times 10 to the minus 12, that's crazy cold, but at this kind of temperature, the typical ability of you to know where the particle is, this thermal de Broglie wavelength, is comparable to how far apart the particles are. And that's when quantum mechanics becomes important. When your ability in principle to know where this particle is, and your ability to, in principle to know where that particle is similar to the space between them, you can't in principle tell them apart. So if you have things that are all, let's say, electrons, those are fermions, you make Fermi liquids, stuff like is in materials, or what we're talking about are bosons. When you can't distinguish them, quantum mechanics is then important. All right? So then we cool to get colder temperatures until such a point that this thermal de Broglie wavelength exceeds the entire size of our system. And what that means is that there is no particle in the system that you can distinguish as having its own special identity. This is a system that's ultra-quantum, when you can't, in principle, tell which atom is which. All right. And this object, when you do it with things that are bosonic, forms a Bose-Einstein condensate. So let's see what I have coming up next. So here are some pictures of what we see in the laboratory when you do this kind of process. Oh, please, stop me more.
You said that if you make them ultra-cold and turn them into ultra-quantum, atoms lose their individual identity. Is that from the point of view of the observer, or do they actually not know who they are?
Well, I would typically claim that an atom is probably not really all that sentient anyway, so its state its state of knowing is pretty limited. What I mean is that if you're talking about like the gas in this room, for example, you, the human being, could go measure where all the atoms are, because I told you the uncertainty in their position is super tiny, and you could say this is atom 1, that's atom 2, that's atom 3. You could put little flags on them. And then because you know physics pretty well, you could sort of see where all these atoms went as a function of time and say, okay, you know, atom 1 with the orange flag ended up over here, and atom 17 with the pink flag went down there. And you have access to this information as a human being. On the other hand, if you have the system that's in this ultra-quantum state, you lack the capability of putting these flags on it. If you insist that you put a flag saying this is atom 1 onto that atom, you have in fact elevated the temperature of the system. You've given yourself a high degree of certainty about where that atom is. And that means if you have a high degree of certainty about where it is, you now have a very bad degree of certainty about its momentum. And that's like saying you've made it hot. So it's about you.
So it's about humans observing.
Well, it's about
to identify.
it's not about consciousness, but it's about the whole, right? Nothing about the world can somehow have information about where that is without simultaneously destroying the fact that it's in this quantum state.
So nothing could know.
That's right. So like,
Just humans.
that's right. Right, so I'm probably, if you want to talk about the philosophy of quantum mechanics, I'm sufficiently aphilosophical that I'm the wrong person. But the idea is that if you had one of these clouds of ultra-cold atoms and some high, rapidly moving, let's say, just piece of gas that happened to be flying by, zipped through it, and that was moving at some velocity in some direction, that's a kind of measurement. And if that atom impacted something in your cold cloud and knocked it out, you've essentially measured where it was. Something's measured it. Maybe you didn't record that information, but the information was nonetheless extracted. All right. So this is kind of for fun. I just want to give you a sense of how cold ultra-cold is. When I say ultra-cold, what do I really mean? I could also talk about ultra-hot, but I don't make anything ultra-hot. I hardly make anything even particularly warm. What this is a logarithmic scale of temperatures on this side, and I've sort of labeled things that happen on those temperatures on this side. So on this scale, room temperature is just slightly above water freezing right there. Okay. So this is a picture of Aspen, Colorado in the wintertime, and that's sort of in the middle of my scale. Now to me, like in my everyday life, liquid nitrogen is really cold. Sort of condensation comes off of it, and you put roses in them and smash it. It's all good times. But in fact, on this graph, liquid nitrogen is almost indistinguishable in temperature from room temperature. Okay, that's 77 Kelvin. At roughly 4 Kelvin, we have the temperature of the microwaves comprising the cosmic microwave background, and that's kind of a distinguishable difference, but not much. And slightly below that, helium-4, can form a superfluid, and maybe you'll hear about that later on. It's pretty cool. And as you continue to go lower and lower in temperature, finally way down here at a nanokelvin, do you see a Bose-Einstein condensate. So it's an incredibly large, small fraction of room temperature. So that's going from about 300 Kelvin to about 1 nanokelvin. So sort of count the orders of magnitude. 300 Kelvin, that's almost the same as 100 Kelvin. That's 10 to the 2. 1 nanokelvin is 10 to the minus 9. So that's 11 orders of magnitude difference. And that's a lot of orders of magnitude. You don't usually see that in life. If you start increasing in temperature, water freezing is there. Iron melting is also a very small difference away, right? And that's like pretty much the hottest thing I've ever made in my life is molten iron. You go hotter than that, you get stellar nebulae, and a nuclear explosion is only on this scale about the same difference in room temperature is to sort of a typical cryogenic experiment. In any case, you could have the sun, a hot star. And the really cool thing is up here. This is the highest temperature that mankind has made. It's a quark gluon plasma. Nowadays, the hottest one is at the LHC. And this is something like 10 to the 12 Kelvin. So that's only 10 orders of magnitude hotter than room temperature. So if you want another order of magnitude, you have to sort of say, what's the extrapolated temperature of the universe? Something like 100 microseconds after its inception. And as a fraction, the BECs are as much colder than room temperature as the universe was shortly after its birth. Okay, yeah?
Is there a place that we know of where something as cold as the BEC exists in nature? Or is it
Nothing that we know of, but we're pretty ignorant that way. Because the whole universe is kind of close to equilibrium, most of the universe is going to be, cosmic microwave background and stuff like that. Seeing anything that's dramatically colder than 10 Kelvin is probably unlikely. But the kind of things that you see in these cold BECs, superfluidity, quantum effects being important, that kind of stuff is thought to occur inside neutron stars, for example, which are crazy hot, but the densities are so high that you get this thermal de Broglie wavelength kind of thing I told you about happening as well. All right.
Hot becomes cold in behavior?
In behavior, right. So particularly in physics, where you try to make things really simple, like 90% of what you do can sort of be categorized by comparing two numbers, right? Or what's the ratio of some numbers? So I'm calling something quantum here for this purpose of this talk, when the typical separation between the ingredients, in a neutron star there are neutrons, here they're going to be atoms. When that typical separation becomes smaller than the thermal de Broglie wavelength, you're going to have this problem of indistinguishability coming in. So the neutron star, why do you see it there? It's really hot, but on the other hand, you've packed the density so high that all the neutrons are just as close together as they can be. So now you're talking about femtometer separations between particles, which can then exceed the de Broglie wavelength.
So, did I hear this right? Neutronium is a superfluid?
Right. So the belief is that under the surface of neutron stars is a crust of superfluid, or a layer of superfluid. Yeah.
Would it be wrong to say cool about that?
As long as you're using it in the framework of awesome, yes. I think it's amazing, and one of the sort of directions of research, if I'm going to sort of step aside from this sort of cool stuff. One of the things that the kind of experiments that my field does, these ultra-cold atoms, is we make systems which have physics that is similar to systems at other scales. So there's a number of researchers who have produced atomic systems that are in the same scaled parameter regimes as a neutron star. So even though they might be working at 10 nanokelvin, the ratio of the thermal de Broglie wavelength compared to the interparticle spacing and the interaction strengths are all tuned such that it's the same kind of physics that appears there.
But where is there a place where you could even do that? Where it doesn't like melt or explode the thing that it's in?
Well, the neutron star, of course, only exists in neutron stars. So it's a great question. One place that some of the neutron star physics can occur is in these quark gluon plasmas. So you learn something about that by colliding high relativistic particles together. But that sort of kaboom, it flies apart. You don't get to learn it for that long. So exactly like you say, if you want to do experiment, you have to find an analog system, a partner system that has similar physics, so you can poke it and prod it and see, does a theory that describes this thing work on the expected or extrapolated behavior of your neutron star? Because you don't have a laboratory neutron star.
See, this is very disturbing because when they first did the Manhattan Project,
Uh-huh.
the initial experiment to divide or explode that first atom, they did not know if that chain reaction would ever stop, and they did it anyway. So now I'm mad.
No, they already knew.
because
They knew it would
I feel
stop.
like physicists are not to be trusted.
Well, no more or less than any other person.
All right.
Physicists have no special claim to trustworthiness.
All right.
But with the, but
Though Fermi did get chided for taking bets on
yeah, so preceding that, Fermi had already built a reactor, for example, in Chicago, and shown that it can be moderated, that you can't have a chain reaction of stable particles. You need things that go to lower energy for that to happen. So I think that one was safe. But yeah, that's right. Yeah.
would a mass of BEC, does it look like a solid? Does it feel like a solid?
Oh, you have predicted 2 slides from now, so I'll do that.
You win.
Yeah, you win the predicting the future contest. Okay, so one more thing I want to tell you about is sort of how do you, even on the surface of it, know by measuring a whole thing, how could you think that it would be quantum. So I'm going to do a thought experiment. We physicists like thought experiments because that way we actually don't need to do a real experiment. So what would happen if you got two balloons or something like that and put them in a vacuum, like in outer space or something like that, and simultaneously pop the balloons and made the rubber disappear all at once, which is a tricky thing. If you could do that, all these little atoms inside these regular old balloons you had would just start to expand and begin to overlap in space. And at some point, instead of having sort of two balls of expanding gas, you'd have one ball of expanding gas. And this is what everyday experience indicates would happen. That's why I can do a thought experiment, because I have a high degree of certainty that's what would happen with balloons. But if you take two Bose-Einstein condensates, as was done in this case at MIT shortly after the first BECs had been produced, two BECs made side by side and allowed to expand, instead of just overlapping, as is pictured here, instead formed an interference pattern. And to me, this is kind of amazing. It's not one C60 atom, like going through a double slit and making a diffraction pattern. This is something like 10 million atoms, 10 million sodium atoms in each of these condensates, forming a diffraction pattern. The scale is not on here, but this is almost a millimeter, which is pretty big. So it's to the scale that you can see. So millions and millions of atoms can be cooled to sufficiently low temperature that they really, really behave quantum mechanically. Okay.
So what, did they get entangled?
I don't know what that means. No.
I don't understand. What are you saying? Can you say that a little bit?
Yeah,
more
sure.
Englishly?
9. Auf Deutsch bitte? Okay, I'm just kidding. So the idea is that the kind of particles I'm thinking, all particles can really fundamentally be described by a wave equation, a Schrödinger equation. And when you're in these incredibly, incredibly low temperatures, all of the particles for these bosons, these BEC particles, are in the same wave function. They're described by the same wave function. Not two, not three, but one wave function. So wave function is, amongst other things, just a wave. So if I have a wave starting here and a wave starting there, and you allow them to overlap, they're going to form an interference pattern just like light does. And that's what's happening in this experiment.
How did they take those pictures?
Oh, I'll tell you about that in a couple slides. And if I don't, if I've deleted that stuff, then you can call me out on it. There'll be some pictures of little yellow circles. If you don't see that like within 5 slides, then I've cheated you.
Wait, back up a second. Why are you surprised that one wave plus one wave equals an interference pattern? Doesn't it do that anyway?
Yeah, but aren't you a little bit surprised that 10 million atoms could behave like one wave? This had never been seen before, ever.
I'm not surprised because I didn't know what to expect anyway.
But this is, I mean, for all intents and purposes, these experimentalists made 2 buckets containing atoms and made the buckets disappear. And every everyday experience of what happens when you do that tells you that the atoms are just going to expand and overlap, right? Right, they're just going to do what happens when you pop those balloons. That's right. So you had to be at this extreme limit of temperature in this case for this kind of thing to happen. And obviously they didn't sit there and say, I got some cold atoms, what's going to happen? They were expecting this to happen once you've made these BECs. Yeah?
And that was done at a constant temperature, so they were still, they didn't raise the temperature to force movement among the BECs.
Yeah, so I'm not sure what I have in the way of trapping here. So what they had done in this experiment is confine the atoms in a trap, which was a combination of some laser light plus some magnetic fields. And they were sort of spaced, I think, maybe 20 micrometers apart or something like that. And then they just turned off the magnetic fields and turned off the laser light. So that's like having a bucket and making the bucket disappear. And now there's no trap at all, and these things start falling because of gravity and expanding because of pressure.
I'm still wrestling a little bit with the apparent nature of the BEC.
Uh-huh.
Which of these statements is more correct?
Yeah.
In your in particular BEC with 10 million constituent atoms,
Yeah.
there are 10 million atoms that have identical wave functions, or proposition 2, the 10 million items have in some sense become one item.
Oh, proposition 1.
Okay.
So yeah, I was hoping at some point we cross the threshold where I'm kind of a mathy guy. So at some point there's like a transition where I suddenly get really mathy. So I'm going to try to avoid that. Right, every single particle is going to be characterized by a wave function. and that's not exactly true. I'm stretching a little bit. But anyway, there is a wave function characterizing all these particles. And when you've made them this cold, it's the same wave function that is characterizing all the particles. So I say they're in the same wave function.
They have not formed one giant atom.
That's right, they have not formed one giant atom. So for example, it would be wrong to say that if you if you performed a measurement of measuring where the particles are, you would not find all the particles here, or all the particles there, or all the particles there, or all the particles there. That's an entangled type state. No, as you measure them one at a time, this image is a type of measurement of where the particles were just once, and you sort of saw it's like measuring the whole wave function, kind of like I showed you a wave function. It's kind of like you measured that whole wave function, or the probability associated with it. So proposition 1 is far more true.
Okay, thank you.
So very Englishy.
Yeah.
Each one of those 10 to the 10 million atoms
Yeah.
is named Dave. And they're each still named Dave.
They're all named sodium. They're all named sodium
So what I
23.
mean is they each have the same equation of that wave function that you were saying. They're identically wave function.
Yeah, I like that
So
one.
let's call that Dave, right? So they're each named Dave, and
That's
they
right.
don't change their name just because you took away the bucket.
That's right. When I took away the bucket, they were all still Dave.
Right.
And Dave sort of indecisively got larger and larger. Each Dave did. But you're right. So then if you wanted to call one Dave, one Sally, one Sue, and one Peter, that's what this measurement actually did. So if you said, after I did the measurement, then you saw where all those atoms were. You gave them individual names. And then it's not, as soon as you took the picture, you've eliminated this fact that they were sharing the same wave function. And if you said, what happened after that picture was taken, they go, pfft. I'll go with you first, because I think you've asked a question.
How long can you keep one of these DACs around?
Okay, so
Before the energy of keeping it that cold becomes.
yeah. So in practice, we can keep a BEC confined for something like a minute. For these cold, for these atomic BECs, it's a minute. Liquid helium can sit in the Dewar for an incredibly long time. A neutron star lives quite a long time. These are all different flavors of BECs. For us, we know the mechanism by which we're losing the atoms. It's not some sort of highfalutin physics thing. It's you're scattering light from laser beams, or background gas atoms, or knocking atoms out of the condensate, or how I said we tried to thwart making crystals with three-body, making the density low. Well, the density ain't zero, so sometimes three particles come together, and you make sort of a molecule and it falls out. So there are intrinsic processes which have nothing to do with it being a BEC that ultimately limit its lifetime. Yeah?
Do you start out knowing the wave function that describes the distribution pattern for each atom or whatever that you are cooling, or do you derive the wave function by looking at distribution pattern afterwards?
Right, so we can derive something about the wave function from pictures like these. So in practice, these experiments are on the repeatability pretty good. So if you measure, let's say I wanted to do something, I'd measure it one time and say, oh yeah, I got my number kind of right, it's about this big, I think that's the wave function I'm making. So then you do it again, probably you made the same kind of wave function as last time. So you say, okay, my initial condition was the same as last time, let's make two of them and put them on top of each other, that kind of thing.
So in theory, every time you cool sodium to this level, you'll have the same pattern, the same wave function, and you can make the generalization about sodium having that.
Yeah, that's right. So to the degree to which you made a good experiment and it's repeatable, you're going to get. I'm protecting myself. Pretty similar results. Yeah.
You made a statement a little earlier, I just wanted to ask you about. So what you're talking about positions, that would be entanglement. This is not that. So this is not an entangled system, whatever that word entanglement means. This is a.
Yeah, I wouldn't want to describe this system as an entangled system. But I don't know what entanglement is, so.
Is there some kind of fight going on there? Because I can tell that's a little sarcastic.
There's a lot of things I don't know what are.
There's a lot of arguments about how do you define entanglement.
Yeah, I mean, do you want me to say something provocative, annoying, and not false?
Always.
If your advisor in the room, be careful.
Oh no, my advisor is about to retire. I graduated a long time ago. But yeah, that would mean no more future letters of reference, which is bad. So the thing I'm going to tell you, which is not false, but is stretching it, is entanglement is not a property of a quantum mechanical wave function. So this is why I'm dodging around it. You can't say, is this wave function entangled, without giving me an additional piece of information and saying, with respect to what? Okay, so in the previous talk, Alan used entanglement a lot, and with respect to what part, he was using your intuition about what does entanglement mean. And it is with respect to where. Right, so if you just give me an equation for a wave function, I can always do something so it doesn't look entangled. So you have to say, is it entangled with respect to this being here and that being there? Okay, so just but I don't want to, I get equation-y real fast at this point with that one.
Just out of curiosity,
Uh-huh.
and I don't want to go off on a tangent, because I want to get back to it. But the words you used just now sounded suspiciously like words I've heard physicists use with respect to frame of reference, with reference frames regarding relativity. I was wondering if there's anything there, or did I just hear a resonance in my own head?
It's, I would
Say no.
I would say it's only at the math level, meaning that, if I have relativity is being described by some four-dimensional vector space, right, with position plus time. Wave functions likewise are described by a vector space. So it's transformations in the wave function's vector space that I'm sort of thinking about when I say entanglement is not a property of a wave function. But it's not the relativistic vector space.
Okay. If entanglement is not a property of the wave function,
Uh-huh.
but entangled pairs exist, then in some sense is a wave function an incomplete description of a particle, since a particle or a thing might be entangled?
Well, when sure, you need to know like where your measurement device is located, things like that. Right, so you have a measurement, I call it measurement basis, right? But you have little things that measure spins or polarizations here and there. And now my measurement is defining the way I'm thinking about entanglement. Compared with reference to the things I can measure, is this entangled? And now I have a question. Now we've got a question. So another way to say it, which is probably not helpful, we're probably going off the increasingly less helpful direction. Yeah. You give me a wave function, and I will tell you a way to write down that wave function in which it is not entangled.
Okay, but if I just give you a wave function, will anything in it tell you if that particle has an entangled partner someplace in the universe?
Well, now you have to tell me about how I'm labeling it. So yeah, if you give me a wave function of two particles, tell me that I have position variables x and y or something like that, then I can tell you what the entanglement of that wave function.
You can't do one without the other.
Yeah, I need extra information. That's all.
Okay.
So an entanglement exactly has to do with the relationship between a wave function and how you would like to express the wave function.
Which in my mind is consistent with the statement I've sometimes heard that once things are entangled, two particles, for example, they're in some sense one entity. And that's why.
Oh, sure, the wave function is one entity. I'm good with that. All right, so I promised to talk about what a BEC would look like, and could you hold it, and things like that. So the answer is no, you cannot hold a BEC. Not the ones we make. So here are some things that you can, at least on the top, hold. And, put that right there, that's brilliant. So this is just a photograph from the internet of a silicon wafer. It's an electronically active device. You build all sorts of cool things out of it, and it's a chunk of stuff. This is another chunk of stuff. I'm sort of marking the density. You can see this is 1,000th the density of silicon or thereabouts. So it's really, you can hardly tell you're holding aerogel, but you can nonetheless, if you're careful anyway, stack books on it and stuff like that. So it certainly is stuff. Incidentally, there's stuff you can make which is like 1/10 the density of aerogel these days. It's some kind of sort of fluffy compound of carbon nanotubes. Unfortunately, it's black. So on this particular slide, you can't see it. So I stick with the aerogel. But anyway, it's sort of stuff. Another kind of stuff, and I'm a physicist, I'm willing to generalize to a pretty large degree what I call stuff. This is a photograph of liquid helium, which is also stuff. It's a fluid. It's a superfluid, but it still has sort of a density that you measure in milligrams per cubic centimeter. So this is the picture I showed before. One of the atomic BECs we make has a couple of million atoms in it typically, and has a density of the scale of hundreds of nanograms per cubic centimeter. So 10 million sounds like a lot of atoms, but it's not so many compared to a mole, which is 10 to the 23. So it's really actually very few atoms. So if somehow someone offered to drop a BEC into your hand, you would not notice it, even though it is only a couple nanokelvin.
But if it's super, super, super cold and it really did touch your skin, would it burn it?
No, there's not enough atoms in it. The heat capacity, the amount of energy you have to give to that BEC to make it warm is just so incredibly tiny you'd never know the difference. Yeah? Oh, I'm going to tell her that right now. Okay, good.
You get there and they go, well.
Yeah. Okay, and later on I also promised I'd tell you how we measured them, so that should be in this section here. And it looks like, based on this rate of information imparting, we're not going to get to gauge fields at all, which is perfectly okay. So when you want to make a Bose condensate of atoms, the first step you have to do is take a look at the periodic table. And it's really, really confusing. So when you're confused as a physicist, you say, what's the least confusing thing on that periodic table? And to me, the least confusing thing is hydrogen. The hydrogen atom is like the physicist's favorite atom. So for a long time, physicists were trying to make Bose condensates out of hydrogen. It turned out that was a mistake. Hydrogen was a little bit too simple to actually effectively make cold. So maybe now 20 years ago or so now, physicists realized that the whole column underneath it, these are the alkali atoms, they're almost as simple as hydrogen, but just slightly sufficiently more complicated that it was actually easy to do what's called laser cooling on them and make, ultimately, Bose condensates. So first you pick an atom. Step one, what atom are we going to make the BEC out of? And what I'll talk about today is rubidium. Now, if you sort of think about atoms all the time, which I do and maybe you don't, atoms come with isotopes. So there's different, rubidium-87, this is the 37th object in the periodic table, indicating that there's 37 electrons involved. That means there's 37 protons involved, but it doesn't tell you how many neutrons are involved. There can be different numbers of neutrons, and those are different isotopes. So you also have to pick the isotope. The one I'm going to talk about is rubidium-87. Okay. Incidentally, so this rubidium has something to do with red. So the first thing is you buy rubidium. That chunk of rubidium, that's, I think, it's probably a 20-gram ampule. It feels kind of dense. It's a metal. It's an alkali metal. This little pocket up here, that's vacuum. These alkali atoms are really kind of reactive. But this is what we start with. This amount of rubidium costs a couple of $100. And that is like multi-scientist's lifetime supply of rubidium if you make a cold atom experiment out of it. Because each time you take maybe a couple of billion atoms out of this thing, which has of order 10 to the 20 atoms in it. So you have quite a number of trials. But let's say that you don't have the money to make a cold atom laboratory, but you did have the money to buy rubidium. The first thing we can say is what happens when you combine rubidium with water? So here's what happens. Okay. Because it's highly reactive. Yeah. So if you just happen to have some alkali metal and you don't happen to have lasers to do laser cooling, this is the next best thing. But instead, we have funding to build experiments that look like this. So this is an experiment that we take that chunk of alkali metal and cool it down to these ultra-cold temperatures. That is the highest grade aluminum foil you can get.
You got any duct tape on that?
No, I don't like duct tape because it fiberizes and makes a mess. But there will be electrical tape. There's binder clips. There's a bunch of common things. The foam core, yeah. So let me tell you how this device works. Let's see. So the length scale of this widget, the depth of the table here is 4 feet, and the length from here to about here is about 8 feet. So it's actually not dramatically different in size than the actual projected size here, maybe only a factor of 2 scale difference. Okay. So let's see. The first thing, I told you that rubidium is highly chemically active. So even if you put it in air, it very rapidly oxidizes. So the first thing we do is we make a vacuum system and evacuate almost all the air. And you might ask, how much is almost all? That's a good question. So in my non-NIST sanctioned units, the pressure in this room is about an atmosphere. An atmosphere is about 1,000 torr. So torr is a unit of pressure measurement. Inside this vacuum system, we go from 1,000 torr to about 10 to the minus 9 or 10 to the minus 10 torr. So that is something like 13 orders of magnitude difference in pressure. The idea there is that once we make these atoms cold, or do anything with them, we do not want them to encounter some other rogue atom running by, like hydrogen or oxygen or anything like that. Those rogues are our enemies, and we need to pump them away. So step one is a vacuum system. So everything inside this sort of tube here, this little chunk of stuff there, that's all vacuum, and that's where the good stuff happens. So this particular vacuum system I first built in 2006, and it is still under vacuum on that optical table, but with lots more widgetry around it. So the idea, now that you got your vacuum, is you start with an oven. Yeah, I said oven. So right here, you can't see it, yes, wrapped in aluminum foil, is a oven where we take this ampule of rubidium, we break it in vacuum. Now it's a broken ampule of rubidium. There's no atoms, so no chemistry happens. And then we heat it up. We heat from room temperature, which is about 300 Kelvin, to about 400 Kelvin. Okay, so on the absolute scale, we heated it a little bit, like by a third. So now we're going to cool it down by 12 orders of magnitude, so increasing the temperature by a third is not a big deal to us. All right, so what does it do when you heat it by a third? It's hot enough that the rubidium starts to evaporate out of the metal form. In fact, it turns into a liquid. And this evaporation process produces an atomic beam. So inside this tube here, we have an atomic beam of rubidium propagating along that direction. Okay, so it's a beam, has a characteristic temperature of about 400 Kelvin. The most awesome thing about this whole gig is that we use lasers, and that's sort of a shining light of laser. You'd think that would heat stuff up. Usually it does. It heats your hand up. It's kind of unpleasant if you have a lot of power. We send a laser beam in the opposite direction of this beam of atoms. So one beam this way, one beam that way. And under the appropriate resonance conditions, the laser light is absorbed by these atoms, and they scatter it. Conservation of momentum. Laser light has momentum. Light has momentum. Photons have momentum. The pressure from this laser field slows the atomic beam down, or the atoms in the atomic beam. So you go from a typical velocity, I mentioned it talking really quick earlier, about 300 meters per second here, and we slow them at the end of this tube by something that seems like not a lot, maybe to 50 meters per second by the time they get to the end of the tube. Okay, this device altogether is called the Zeeman slower. I've told you about half of its functionality. That's enough for here. Okay, so we're relying on laser light pushing on atoms to slow them down. This works if you add more lasers in more directions. So once you've slowed it down enough with the Zeeman slower, we come along with 6 lasers along the Cartesian directions, sort of like that, to push along every direction. And this beam of atoms is finally slowed and captured right there. So the beam typically has a flux or a rate of atoms of about 10 billion atoms per second slowed down this tube. So after a second or so, we capture of order 1 to 10 billion atoms right in the center there. So you have lasers along all the directions, scattering light in every possible direction. Every time an atom tries to move or escape, it gets pushed back, it's captured, it's slowed. Okay? So this device, this one's a Zeeman slower. This one that points along 6 directions is called a MOT, or a magneto-optical trap. And again, I've sort of given you only the vaguest outline of how it works, but it's radiation pressure from light that we use to take the atoms with their initial 300 Kelvin temperature and cool them in this particular apparatus at that stage to a temperature of maybe a millikelvin. Okay? So already we've done an enormous amount of cooling. And where I work I'm employed at NIST. NIST has a huge investment in laser cooling for the reason that it's important, for example, for modern atomic clocks. Just taking out this motion of particles is really critical for timekeeping applications, for example. And for our physics experiments, it's just the beginning. So we're shining 6 lasers, tuned to the appropriate atomic wavelength. You know how I told you rubidium had a Latin name ruby? Well, that has to do with the color of the light that interacts with it. It's a ruby red light. In fact, you can't see it. It's almost infrared. But my iPhone can. So this is a picture of a laser-cooled cloud of a couple of billion rubidium atoms. at this point whose temperature is of the order of magnitude of millikelvin. All right? So that's pretty awesome. We have a beam, we have an apparatus with lenses and with metal and currents and stuff like that. We captured a bunch of atoms. So in a second or so, we capture of order a billion atoms whose temperature is about a millikelvin. Now a millikelvin, that's 1,000th of a degree. That seems awfully cold. Unfortunately, at a millikelvin, the thermal de Broglie wavelength is still much, much smaller than the separation between these particles. We are not close to a BEC, so we need one more step. Let's see, so laser cooling was a technology that was invented for a bunch of atoms, not ions, in the early 1980s. That's the slowing. Later on in the 80s, this magneto-optic trapping was invented. Then even later on, the next thing I'm going to display was introduced, which is going to be evaporative cooling. So sort of, you're sitting, you're really frustrated because you can't get stuff cold enough. Laser cooling isn't getting cold enough. So you sit down and you drink a cup of coffee. And no doubt the inspiration was at the same time you were frustrated that you had cold coffee, you were delighted because your coffee got cold. And in fact, that's how we can cool these atoms to get lower temperatures. So what does evaporation do as a process? You have a chunk of stuff like your coffee, and every now and then, the most energetic atom is kicked out, right? That's why it left. It had more energy. It overcame gravity, it overcame surface tension, and it isn't there anymore. That means that on average, all the other atoms in that collection have less energy than they had before if you took out the most energetic one. So on average, the typical energy is decreased. And this is the process by which we cool our atoms from temperatures of order of 10 to hundreds of microkelvin, finally into the nanokelvin regime. And now I'm going to tell you about measurements and all that. So we make a trap for the atoms. And this particular trap is depicted for laser light that has captured them like a bucket in space, levitating the atoms. And we simply make the trap less and less deep, so that every now and again, the most energetic atoms leave, then they collide with each other. They find out, oh, I'm colder now because my average energy is decreased, and you keep doing that. Yeah?
Since they're all in this controlled environment, why is any of them more energetic than the other ones?
Okay, so what you're asking is why aren't they doing exactly the same thing? If they were already doing exactly the same thing, you would already be at zero temperature.
Why?
Because that's what zero temperature is. It's no remnant information in the system. If they were all, our goal is to make them do all the same thing. So all this whole dancing about is trying to make them do the same thing. So in a slightly more physicsy way of saying it, which is probably the opposite of what you really want me to do, if I tell you something has a temperature, when I tell you something has a temperature, I'm telling you that inside of it there's a range of velocities that are present. So I started out with a large range of velocities, then my laser cooling process made a much smaller range of velocities, and now I need to make that range of velocities tinier and tinier. And associated with that is a decrease in energy. Yeah. So what we're doing is we're just chucking out the most energetic atoms, and since you took out the most energetic one, the average energy decreases. And these images are measuring more or less the range of velocities or momentum present in the system. And as it gets narrower and narrower, this is representing to you the decrease in mean velocity and therefore temperature, until from here where it looks like a blob to here where it looks like a nugget. That's when you form the Bose-Einstein condensate. So I think earlier you asked, what is ultra-quantum? Well, this is not particularly quantum. This image, if you look carefully, you'll see it's a blob here with a different shaped blob on the inside. That guy's starting to get quantum. Some of the particles are starting to get into the same wave function. And here, they're pretty much all in the same wave function, ultra-quantum. All right. So I think my next slide has some more hoopah about what we're measuring. So what we do is that we have the atoms in this little bucket in space, and we turn the bucket off. And when you make the bucket disappear, everything starts moving in a sort of marbly sense of doing it. If my bucket was initially the circle, every particle maybe had a velocity, maybe not. They start moving, and after a while you take a picture and say, where did you end up? And that's sort of asking the physics question. If I said, where did something end up after it moved for a while, I'm really asking you what was its velocity. Because its velocity is going to be, where it is velocity times time. I've got my distance. All right. So these pictures I'm showing you here are really measuring the type of velocities that are present in this system. And physically, how did this measurement process work? We had these chunk of atoms. We've got all these lasers all over the place. And I told you the lasers pushed on the atoms. well, if I'm shining a laser at something and scattering laser light in all these crazy directions, I must be taking light out of the laser beam and putting it somewhere else, all those other directions. So what we do is we measure the shadow the atoms cast on the same lasers, basically, we use for the laser cooling. And by looking how deep the shadow is, what fraction of the light is removed, I learn about the density of atoms. Okay, so that's our measurement process, is shadow imaging. So you do shadow puppets, you can do VECs. All right. There's one more thing I just wanted to show you because it's fun. We're not going to get to any of this in this talk. So I told you we do this expansion gig here and sort of learn about the velocity of the atoms. Atoms also have other properties, like they're kind of spinning. They have spin. So maybe you've heard about quantum spin, maybe in the framework of entanglement. Well, one of the earliest experiments that was done in physics to sort of really confuse people is called the Stern-Gerlach experiment. And in that experiment, a beam of silver, I guess, was sent through a region where there's a magnetic field gradient, so an inhomogeneous changing magnetic field. And Stern and Gerlach, who incidentally happened to smoke, noticed that when the silver atoms went through this, they split into multiple blobs. And these blobs are telling you about how the different ingredients are spinning, or their angular momentum. So this is now called the Stern-Gerlach effect. And we use the Stern-Gerlach effect also on our cold quantum gases to learn how they're spinning. I sort of think it's neat that an idea at the inception of quantum mechanics that was used to prove quantum mechanics is really weird is now used as an everyday tool in our laboratory. All right. I'm going to go ahead and just stop now, because you know what? Nothing's going to make sense. Emily says I have 5 minutes left. I'm just going to introduce 5 minutes of confusion at this point.